In this, our final lecture on sequences, we prove some more facts about lim sups and lim imps. These results will be helpful when we discuss infinite series. Theorem. Suppose the sequence Sn converges to S greater than 0, and Tn is any sequence. If lim sup Tn equals positive infinity, then lim sup of the product sequence Sn times Tn is also positive infinity. Similarly, if lim sup Tn equals negative infinity, then lim sup of the product sequence is also negative infinity. And finally, if lim sup Tn is finite, then lim sup of the product is the limit of the Sn's times lim sup of Tn. Proof. For part 1, if lim sup of Tn equals positive infinity, then there exists a subsequence, Tnk, diverging to positive infinity. Now consider the sequence Snk times Tnk. This is a subsequence of Sn times Tn. Since the sequence Sn converges to a positive number, this subsequence must diverge to positive infinity. In fact, we proved exactly this a few lectures ago. For review, let's recall how it's done. Let m be greater than 0. There exists a positive number delta and an integer L such that for all n greater than L, Sn is greater than delta. This follows immediately from the fact that lim Sn is positive. Since nk is greater than or equal to k, Snk is greater than delta for k greater than L. Since the subsequence Tnk diverges to positive infinity, there exists k1 such that Tnk is greater than m over delta for all k greater than k1. Therefore, for any k bigger than both L and k1, we have Snk times Tnk is greater than m. This proves that the subsequence Snk times Tnk diverges to positive infinity. Now, to finish up, we have that positive infinity is a subsequential limit, which implies lim sup of Sn times Tn must be positive infinity, because lim sup is the largest of all subsequential limits. The argument for part 2 of the theorem is similar to part 1. For part 3, let beta denote lim sup of Tn. We'll prove the two inequalities, S times beta is less than or equal to lim sup of Sn Tn, and S times beta is greater than or equal to lim sup of Sn Tn. Since lim sup of Tn equals beta, there exists a subsequence converging to beta. Therefore, the sequence Snk Tnk converges to S times beta. Remember, the sequence Sn converges to S implies that all subsequents of it converge to S as well. So S beta, being the limit of Snk times Tnk, must be the lim sup of Snk times Tnk. The last equality follows because the sequence converges to a number if and only if the lim sup and lim imp also equal that number. Now notice that a subsequence of Snk Tnk is still a subsequence of Sn Tn. So any limit of a subsequence of Snk Tnk is automatically a limit of a subsequence of Sn Tn. Thus, the largest subsequential limit of Sn Tn must be at least as big as the largest subsequential limit of Snk Tnk. In short, lim sup of Snk times Tnk is less than or equal to lim sup of Sn times Tn. Now, putting our two equations together, we obtain S times beta is less than or equal to lim sup of Sn Tn as desired. To prove the second inequality, note that since the sequence Sn converges to the positive number S, there exists an integer n naught such that Sn is greater than 0 for all n greater than n naught. Now redefine the sequence Sn so that Sn equals 1 for all n less than or equal to n naught. By changing finitely many terms of our sequence, we will not affect any limit calculations, including lim sups and lim imps. But now the sequence Sn is a sequence of positive numbers, and so the reciprocal sequence 1 over Sn is well defined. Certainly for any n, Tn equals 1 over Sn times Sn times Tn. So beta, which is the lim sup of Tn, is also lim sup of 1 over Sn times Tn. The sequence 1 over Sn converges to 1 over S, which is positive. So, by the first inequality proven above with Tn replaced by Sn times Tn, we get that 1 over S times lim sup of Sn Tn must be less than or equal to lim sup of 1 over Sn times Tn. and that's just beta. Moving the s to the other side gives lim sup of Sn times Tn is less than or equal to S times beta. That's the second of the two inequalities we wanted. Putting these inequalities together finishes the proof. The next theorem will help us understand the relationship between the ratio test and the root test for infinite series. Theorem: let Sn be any sequence of non-zero real numbers. Then the following inequalities hold. Proof: first observe that the middle inequality is immediate. For any sequence, the lim_inf is always less than or equal to the lim sup. As for the other two inequalities, the book proves the one on the right. We'll take care of the one on the left. Notice that the absolute value of Sn to the 1 over n is always non-negative, so the lim_inf must also be non-negative. Thus, if the lim_inf of the absolute value of Sn plus 1 divided by Sn is 0, then we're done. Otherwise, the lim_inf of the absolute value of the ratio of successive terms is positive. We'll show that for all positive real numbers r, if r is less than lim_inf of the absolute value of Sn plus 1 over Sn, then r is less than or equal to lim_inf of the absolute value of Sn to the 1 over n. From this, the desired result would then follow. So suppose r is greater than 0 and less than lim_inf of the absolute value of Sn plus 1 over Sn. Then for some k, what we call inf sub k of these ratios must be greater than r. Therefore, for all n greater than k, r is less than the absolute value of Sn plus 1 divided by Sn. Now here's the trick. Write the absolute value of Sn as follows. We have n minus k plus 1 fractions, and each is greater than r. So this is greater than r to the n minus k plus 1 times the absolute value of sk plus 1. Let a denote r to the negative k plus 1 times the absolute value of sk plus 1. Notice that a is greater than 0. We've shown that for all n greater than k, the absolute value of Sn is greater than r to the n times a. In other words, for all n greater than k, the absolute value of Sn to the 1 over n is greater than r times a to the 1 over n. So for all n greater than k, the elements of the sequence absolute value of Sn to the 1 over n are greater than the elements of the sequence r times a to the 1 over n. Applying lim_inf, which will preserve the inequality, we obtain lim_inf of the absolute value of Sn to the 1 over n is greater than or equal to lim_inf of r times a to the 1 over n. But we showed many lectures ago that a to the 1 over n converges to 1. So r times a to the 1 over n converges to r. Hence, putting our results together, we get that lim_inf of the absolute value of Sn to the 1 over n is greater than or equal to r. Since r was an arbitrary positive number less than lim_inf of the absolute value of Sn plus 1 over Sn, we can conclude that lim_inf of the absolute value of Sn plus 1 over Sn is less than or equal to lim_inf of the absolute value of Sn to the 1 over n. Finally, we mention one rather immediate corollary of this theorem. If the limit of the absolute value of Sn plus 1 over Sn exists and equals L, where L can be finite or infinite, then the limit of the absolute value of Sn to the 1 over n is also L. Proof: since the limit of the ratios is L, the lim_inf and lim sup of the ratios must also equal L. Plugging this into the inequality given in the previous theorem, we see that the two outer terms equal L, and therefore the two inner terms must equal L as well. In the next lecture, we'll begin our discussion of infinite series.